Okay, hello and welcome. Here we are in lecture 12. So as you can see from the title, we're going to be wrapping up our Lightning 2 or functional programming, kind of these crazier constructs. And we're actually going to go in a little bit of a different direction, and that is to consider not only some additional collective operations with these things, but do something called pattern matching. We're going to see chances where we actually can do some really cool stuff in the language in Scala, which a couple languages have these features, but maybe you haven't seen it before, and so it's pretty cool to see some of these things kind of applied. Today's actually mostly Scala. It's actually not going to be much chisel yet. I'm going to chisel in the next lecture to start applying this. Okay, so as I said, we're going to cover a couple more collective operations, flat map, filter, sum, and then we'll get into pattern matching. So I'm going to go ahead and load up our notebook. Great. Okay, so first, flat map. So as the name might imply, it's like map, but there's a flat there. What is flat? Well, it's actually like the term flatten. So you may not have used this operation, you may not have a need for this operation, but the flat operation, when given a collection of collections, dissolves the inner collections and merges them all together, right? So to kind of see what we mean, let's say, for example, we have, I'll kind of turn this code on progressively, right? So, if you have this L, which is, a range, sure, we can do that. Or if we use, seek.fill, of course, we can build, a seek of two instances of the number 3. Sure, we can do that. So now this next line, what are we going to do? We are going to print the result of mapping L onto this operation where we're going to generate a seek of whatever the number is, that many times and that many things, right? So in other words, we're going to get a list of, 0, 0 times, 1, 1 times, 2, 2 times, 3, 3 times, 4, 4 times, right? So, okay, cool. So the reason why I have this example is not because the exact numbers matter, it's more it's because what we wanted was a collection of collections. Here we have, a vector on the outside and a list on the inside, but you can think of both as seeks, so there's just more concrete classes. Okay, that's the point. We have two collections, right? We have an outer collection and kind of inner collections inside the elements, right? And so we could take that result and let's say I didn't want two collections, say I just want one list, right? Well, we could call this dot flatten operation, which will combine them all together. Or we can call flat map, right? So flat map's gonna give us the same result. And so the way to think of flat map is like a generalization of map such that rather than returning a single element, you're returning a collection and you're appending it to the existing collection so far, right? So you can think of map as, applying a unary function to every element and you get, element in, element out, and the element out is all put together in a collection. It just so happens in this case that the element in was a collection or a number, but the element out was a collection. So you had a collection of collections if you just did map. With flat map, you're now saying, okay, element goes in, collection comes out, and rather than making a collection of those, you append those all together, right? So I think I have a diagram on the next slide that kind of showed us. For example, if you run map, like I said, we have, in this case, you're running map on a collection. It could be a single element, sure. When you get collection on the other end, you get all these boxes, right? Collections of collections over here. With flat map, we're going to start appending this all together, right? That's kind of the whole point. Okay, so maybe you're wondering how often this occurs or why this matters. The reason why we're doing this is that you'd be surprised how often you end up with variable numbers of things returning. And so a very common trait in my code is actually when you have a situation where the number of things you're returning in this collection could be 0, right? So you have something that comes in here and it could be, the result could be, 0 through 3 elements long. And so actually flattening together is what you want. And so there's some more examples to see throughout this course where we use flat map. And so that's kind of where we're covering this one. We did cover this one later in our list of, techniques because, it's not as commonly used, but it's still used sometimes. So you want to be aware it exists. Cool. Questions on flat map? Okay. So let's go ahead and move on to another step, which is something called a predicate. And so something we're going to need in order to use some of these other operations. So a predicate is a unary function. It takes in an element and it tells you yet true or false about the result, right? So you can imagine for things like filtering, this is really important, right? So if I want to filter everything, how might this work? Well, I can make a function is even, given a number. We can, of course, by using mod 2, we can see is it even or odd. And we can go ahead and apply some things. So let's go ahead and maybe comments going to stop momentarily and just run this on the range. We can see, for example, if we filter everything, if we call filter with is even on this collection 0 through 5, we get the even numbers, right? And so that's pretty cool, right? So you can use some of these other alternatives, right? We could, let's say, want the odd numbers. I could apply the function and say I want to apply the negation of the function. So that'll give us the odd numbers. Scala being Scala and having rich features, we can just say, instead of filter, we can say filter not, and it negates the predicate for us automatically. That's pretty cool. So that's filter. This is really helpful. You can imagine you have a collection, you're just trying to grab things, right? You can see how this kind of works. For these collections, collective operations, you can have these collections full of things. You can map them, you can flat map them, you can for each them, you can filter them, you can kind of keep tossing things around all at once. So you kind of see if you get more familiar with these, you basically don't need to write for loops anymore. You basically can just constantly have these collections that kind of constantly be passing things around and appropriately mapping or filtering, etc. Now, one scenario to make them up is you may say, you know what, I actually don't want to filter. I want to know or check some property about these collections, right? And so there's both these existential predicates. You have both there exists or for each, right? Basically, the for all and exists, right? And so for all is true if and only if the predicate we say is true for all elements, right? So, for example, with the collection I've given, are they all even? And the answer, of course, is no, right? Now, if I took the even ones and then tried that, hopefully it's going to say true, right? Yes, right. So, cool. Yeah, so for all, like I said, it applies this predicate to every element. And if all the results are true, great. Exists is true if any one of them is true, right? So if you want to say if any one was a problem, it pops up, right? So for example, are there any even numbers in there? Yes, there are, right? What if I took the odd numbers, which was this one, right? So none of the odds should be even. Oops. Correct, yeah. So cool. You can see it's kind of pretty handy, right? Between filter for all exists, really quickly, really concisely, kind of expressing about what we're doing. You can see that it's actually, despite the conciseness, actually it's a certain amount of formality what we're doing, right? We can kind of very quickly kind of establish these things. You can imagine start trying to reason about your program, rather than having some sort of for loop with mutable state, wondering about when does this get updated, how do I prove this is correct, maybe some sort of thing involving induction or something. We can have this much more concrete, high confidence building block when it's possible to match this. Cool. Questions? Okay, cool. All right, well, let's keep going. So for regards to filter, we're going to visualize in this case. So remember filter, if there's nothing produced, it doesn't pass the filter, we just don't include it in the set, right? So if in this case it's true, it goes through. This case we applied the function, it was false, we don't include it. This last one was true, so we include it. So that's filtered. Do I have one of the other ones? No, I don't. Okay, cool. So to kind of put all these together, I have this example for quite a bit of code, but we can kind of talk our way through it. So we'll go ahead and momentarily comment some stuff out so we can kind of see what we're doing. So our goal is to list out prime numbers. So what technique we're going to use in this case is a Seive. Technically it's a Seive or Erasmus. So what we're going to do is we're going to say, hey, we're going to make a function multiple of, which will tell you if B is a multiple of A, right? Now you may notice that I chose to break up the arguments into two blocks, just that currying we talked about last week. And you can see the reason why I did that is now we can apply filter, right? So we can say, given a list of numbers and a specific number, we can remove all the numbers that are multiples of it, right? So the way we do that is we're saying, remove anything that is not a multiple, right? So everything that is a multiple is going to get dropped because it's a filter not. So yeah, if we go ahead and activate this code again, right? So we can see, for example, all code um, that is filter not a multiple of 5. We can see, for example, up to 100, these are all numbers that aren't multiples of 5, right? So we've kind of done that, and this is, just a handful of lines here. We kind of put this together. Or, in this case, we actually made a function for this, right? So we can just call remove multiples of, right? So we actually don't even want to have this other one distracting us, right? It's the same result. And so one thing to notice here, right? So here's this curried function, right? So remember, I give it the x first. So after applying this x, it's still a function that takes in one more argument. That's what is going to be used by the filter not call. Cool. Questions so far? Okay. Yes, correct. In this case, it is. So the question is, so all nums is a range. We did a filter not, and we got a vector type. So to be quite honest, I don't remember which types produce which things. When I write code intentionally, I use seek. Seek is an abstract class, so you need to have a concrete type to be instantiated. And so the most common ones are both list and vector, as the names would imply. Uh, Vector is contiguous array-like internal representation versus list is perhaps more linked list-like. Um, that's not quite true. The list implementation in Scala actually is smart enough to actually batch together multiple data elements per linked list top. So that way, rather than doing one pointer reference per element, you do like one pointer reference every like 16 elements, something like that. So it's not the worst, but yeah. So that's the status. Now, in terms of Scala code recommendations, you read a style guide. They usually recommend you not using seek. They usually recommend you saying list or vector, or being very intentional, knowing your algorithms and what you're doing. Um, I've kind of made the choice to go seek centric when we write our chisel code because number one, it's simpler to have one class rather than two classes and something like that. But also usually when we have these in chisel, because this is going to eventually turn into hardware, usually seek's not very large, right? Usually it's like, 8 elements, 16 elements, not that bad. So I think for that reason, whatever the compiler chooses, whether the compiler chooses to use a vector or a list as a concrete type and implement this abstract type for you, that's usually fine. Now, as an interesting counterpoint, for some of the research in my own group, we have a large Scala-based tool we implement. And that tool, we actually do occasionally handle millions of elements. We still use seeks, and we've occasionally gone in and profiled, okay, if you change these seeks to either list or vector based on how we use it, it's a small difference. And so from a code management point of view, uh, I've chosen to continue using seeks to keep our group sanity, rather than just mismatch. And so, yeah. So yeah, you can see in the code in this course, I always just call seek, and when we look at what it's actually returning, you occasionally get vector or list as things. Now, range is a little different. Range isn't always fully materialized, right? Sometimes it can be lazily evaluated if it's a range. Cool, great question. Okay, so remember where we are. We built up these two functions, and we can, uh, find something as a multiple of something, and then we can use this by doing currying, to remove all multiples of something. Great. So now our Seive, you can see, this next block, we're going to go ahead and do this recursively. And what we're going to do is we're going to take all the numbers and go through them one by one. And whatever the head number is, well, we're going to say that one is prime. And then we're going to remove all multiples of it from the remainder of the list, right? So in other words, we're going to say, hey, so this one in front is, the head, right? So, okay, whatever the number is, that's going to be part of our final result. And then we're going to call ourselves recursively on the tail of that collection, right? And we're going to remove everything that's a multiple of me, right? And so if we do that, we'll go get the function first and go ahead and run this. We're going to get the prime numbers. So that's pretty cool, right? We said the prime Seive in what? 6 lines, right? Um, Pretty cool. So here we are applying the few things we just talked about, right? We saw an instance of the currying from last week. We saw filtered not. You can see how some of these filters are pretty cool. Great. Okay. As I mentioned previously, I took the time to put this down on a slide. The collections of Scala are pretty rich, and so they have a lot of things built in. So we talked about, oh, you can do reduce on a lot of different operators, like plus, times, min or max. And it turns out that for many collections, if your type meets certain properties, you can just call these operations for you, for example. So yeah, if I have the numbers 0 through 5, 0 through 4, of course, add them up, that's 10, 0, 1, 3, 6, 10, yep. And of course, you can multiply them together since there's 0. That's going to win out. Take the min, 0 is also going to win out, and then take the max, and then eventually 4 is going to win out. But I showed this slide mostly to kind of remind you that, yes, you can call reduce. Also, sometimes in Scala, there's built-ins that you may not think the language should have, and they just have it, and it's convenient, and it's nice and concise. And I want to remind you folks, I said these operations are built into the collections, and so that way, yeah, you can just call them when they're there. And this is why they have this entire fancy hierarchy of abstract types, is that in many cases, the convenience function we're calling, like .sum, is calling the plus operator, which, depending on the nature of the element you're holding in collection, has its own implementation, right? Cool. Okay. We were just racing through today's content. Yes, great. Yeah, so the question was, why does LSSum not work with the chisel uint when I tried to do it for the reducer? That's a great question, and I'm only 80% sure on this answer. So, um, worth remembering that when you add things in chisel, what's happening? There is the result, which we capture usually in a val or something. Oh yeah, we're capturing this thing in a val. And then there's the side effects it's doing in the chisel design graph to connect things. And so my best guess of what happened in that case was somehow um, the addition was not properly exposed for that. And that was caught by the compiler rather than runtime because the chisel uint type did not meet the numeric requirements, I guess, for sum. Best guess, 80% chance. Uh, okay, cool. So we're going to keep, we talked about trying to keep building stuff up, right? So we were kind of playing around with stuff. So for example, uh, let's try and do some linear algebra with all these collections in parallel, right? So linear algebra is often kind of the way to think about math in terms of what's the maximum parallelism kind of expressiveness. And here we're using functional programming, we can kind of put two and two together. So for example, maybe before I let the other code run, I will just define mat, and you can see, for example, yeah, well, what is mat? Well, in this case, we were calling tabulate, which we've covered before. Interestingly, you can call tabulate with multiple dimensions, right? So if I call, tabulate with just one dimension, that's what we've seen before, right? That's what we were used to. We can call it with multiple dimensions. It's actually going to iterate through both in nested fashion, right? Iterates to one, then iterates to the other, nested. So we're getting two numbers. So in this case, we can put these together, right? Okay, so 0 plus 0, 0 plus 1, 0 plus 2, 0 plus 3, 1 plus 0, 1 plus 1, 1 plus 2. So you can see it kind of falls together. So these numbers are the sum of the coordinates. Cool. So this is just to get a matrix for us to play around with. But our goal is to multiply the two together. So in order to do that, we have a couple options. So in this case, we're choosing to do it in one way. So the way we want to do is we want to eventually get to the point of computing each output cell one at a time. It's kind of the easiest way of doing it. So that way, the reason why we're doing in this case is by computing each output cell one at a time, we don't need to worry about accumulating partial sums and overwriting things with mutation, right? So in order to accomplish that, we do a couple things, right? So when we're computing that cell, remember how you do matrix multiplication? You take a row of the A and a column of the B, and then you compute the dot product, right? And so for the dot product, we've written that in one line here using stuff we've covered in the last 3 lectures, right? So given two sequences, right, these are basically like two vectors, we can combine the elements of a zip. For each of those pairs of elements, these tuples, right, basically an A of I and a B of I, we can multiply them together. So now we've taken the pairwise products of these two vectors, right? And then we can add them up. And yeah, the pairwise products followed by a sum, that's a dot product. Okay, so we have dot product. And let's kind of go through some of our other operations here. So for example, in order to multiply, we tend to want to multiply a given row times a given column. So we want to be able to extract a given column out of the matrix. And so to do that, given our matrix in this case is just a 2D seek, we're given a column index, I, and then what do we do? Well, we go through the matrix, and so when we go through the matrix, we're going to define, we're doing things in row major order, that's an arbitrary choice. We just as well have done this in column major. So we're going through row major. That means each seek represents a row, and then the elements within that seek, correspond to a column, right? So yeah, we're going row by row, and for each row, we're going to grab the data at that index to get that column, right? So we do that for all rows, then we get all data for a given index. So you can see, for example, when we call this on the original matrix, that I want column 1, that's right here, this column. So yeah, that pops up down here. Cool. Okay, so putting everything together, we want to compute a matrix multiplication. So we have two matrices, A and B. For now, for simplicity, we're doing everything square. And what are we going to do? Well, we're going to map on the rows of A. And for every row of A, we are going to map on each element, right? So it's two maps, right? A map and a map. Remember, this kind of, matrix is two-dimensional. So we're mapping one for each dimension. This outer map is going row by row. This inner map is going column by column in that row. And so, okay, so given that, we started off mapping on rows. So we have a row of A. And then we wanted to know the index of where we were. So we zipped up an index and then applied maps. So, okay, so we have each element in the row of A and then an index. So what we can do? Well, we can multiply that row of A with the corresponding column in B, and we'd use that grab column function we just talked about. So we kind of put together these abstractions and constructs. And the result is, yeah, we've written up a matrix multiplication function that hopefully does the right thing. Maybe I should go ahead and make that a print so that way it comes to the top. Right? Oops, actually no, we don't like print because prints don't, the print doesn't preserve the, yeah, you can basically see that that's the function down there. It's the result. And so there's a lot of kind of operators packed in here. I think we've been talking a lot in this course about occasionally being judicious with these FP operations to make sure we're not losing readability or being super brittle. This is the most extreme thing I'm going to try and do with FP stuff in this class. This is kind of showing how far we can go with it. We're going to be asked to do something very similar to this on the first problem in the homework. It's actually in some ways taking this code and generalize it. We can all pause for any questions right now. So this is the way that, me trying to write it with functional programming I came up with. In a prior offering, some students asked me to try and do it in other ways, and that's in requests, and so we tried this other way, it was shown down below. The code's more concise, and actually in this case, we're using the tabulate option again, right? So remember over here, we use tabulate to kind of iterate through the 2D space of a matrix. With this approach, we're going to do the exact same thing. We're going to use tabulate to iterate through 2D space of the matrix and the output matrix in this case. So, when you multiply a matrix, right, it's going to have, the number of columns in A by the number of rows in B, right? That's what we're saying. Okay, so we're going to go ahead and iterate through that space. So we're going to get, 2D coordinates, right? And given those 2D coordinates, we want to compute the product, right? Well, we want to get the right row of A and the right column of B, and then we get it. So some folks find this other version maybe more clear. Yeah, and you get the same result. So I and J come from tabulate. So tabulate, if you remember, the way it works is you give it a dimension limit, and then it gives you 0 until that number. And if you give it 2 numbers, yeah, it's actually a great question. So maybe the best way to get that across is what if I go ahead and say seek.tabulate 2 by 3. So we're going to get these 2 things coming into us. And then, just so we know what's going on, we're going to print I and j, and then we are also going to, sure, we can also say something like I times j is going to be the resulting matrix, right? So the reason why I ran this is to get the result down here, or it's right here, I guess. The key thing is more the iteration space, right? So you can see that we're iterating through the space encouraged by this, right? So this is the outer loop, this is the inner loop. So for every iteration of this, we do all iterations of this, right? So we're kind of iterating through this space. And so this generalizes, right? We can say for the, and then, it keeps going. This is one of these operations where it's really helpful for us doing kind of these math tricks, and occasionally in hardware this is really helpful. Heaven knows where this comes up in regular purpose programming, but Scala includes it and it's great. And so it's kind of fun. This is a tabulate function, yeah. This is a way to kind of generate a sequence and the kind of automatically fills it in. Cool. So yeah, so this map mole can be a little complicated. We kind of talked our way through it. And you can see how we did this, right? Rather than doing this all at once, right? We kind of built up abstractions we can reason about, right? And use those. For example, we know we're going to need a column and do the dot product, so let's go ahead and make a function that can do the column, right? Or we know we're going to need to do a dot product, make a function that can do a dot product. You can imagine if we didn't write the code this way and instead combine all this, it would be horrifying, right? I mean, I can do that right now really quickly. It might all realize how horrible the idea it is, right? So for example, instead of doing this, we did the dot product, right? So it's going to be gross, right? In this case, I might choose to put this case on the prior line because we're going to run out of space in a hurry. All right, so A is now row of A. And then B is going to be, well, for now we can leave grab call in there. But we can see already, oops. Yeah, okay, there's the result. So that works, right? And so you see already, if you thought this was hard to read, this is even harder to read, right? So this is kind of me showing a pattern of what's going on. And so even here, like this, hint of what's going on with grab call is helpful, right? If I took that away from us again, it would get even scarier, right? So call is call index. So I would say, if I was to totally remove this, right, I would say B map row, and then this is call index. Yeah, oh my gosh, right? Yeah, heaven knows what's going on in this code, right? Like, if your coworker wrote this and said, "Bro, can I get a code review?" I would say not pass, right, on the code review, right? And so, like I said, so this is kind of showing like sometimes it's really easy to get carried away with these functional operators, but the other thing is it's not documenting, right? You start chaining things together, like the contents are ambiguous, right? So having names to things to try to help you guide what's going on really helps. And so yeah, so do one operation at a time. Here I did it with functions. You can imagine sometimes you can do it just as a val. That's fine. But the idea is, yeah, break it up, right? As scary as this looks, this is still way more readable than that thing I made below, right? Cool. Okay. I think it's the last I have on the FP stuff. Yes, it is. Yeah. Oh, yes, good question. So why is there a case down here and not up here? Because it works without it, I would come to the conclusion this is superfluous. So we can go ahead and try and confirm that. Um, yeah, that is superfluous, right? So as a reminder about the cases when it comes up, um, you need to use case when the compiler can't otherwise recognize the difference between things. So to be clear, in this case, no case pun intended, this is a tuple coming in. So single argument, two fields. So we're using case to pattern match onto the field, which actually is the next slide about pattern matching. Down here, there's actually generally two arguments, right? There's one for each dimension. It's not a tuple, it's two arguments. And so, yeah, this is one of these things where, as a daily Scala programmer, sometimes you remember which one's which, sometimes you forget. Sometimes you try it, the compiler yells at you, okay, forgot case, and you put case in there and it works. But like I said, semantically what's going on is just that, yeah, it needs to be able to tell the two apart. In this case is superfluous, and it's not really telling me that, but maybe if I was using IntelliJ, it would tell me that. Yeah, good observation. This one over here, for example, I'm pretty sure is going to be really required. If I delete that, it's going to tell me. Yeah. Because in this case, you really need it when it's a tuple. When it's a tuple, you definitely have to have it, because otherwise it's getting a mismatch in the number of arguments. A tuple is a single argument. It just has multiple fields using case to pattern match those fields, versus down here, it actually is generally multiple arguments. We actually don't need to have the case. Cool. Cool. Great. Great. Okay, let's go ahead and talk about pattern matching. So we're going to kind of build through in multiple steps. In the simplest case, we are just going to show match, which looks a lot like something you may have seen in Switch in other languages. The difference is we can kind of start doing some fun stuff with it, right? So for example, let's say we're matching on this variable x, like it's like a switch x. So yeah, you can do simple direct case matches. Okay, this is exactly equal to this. All right, if it is, yeah, we're going to return 0. Sure. But you also can do ors, no problem. So if it's going to be 1 or 3, we're going to get the same, behavior. No problem. Okay. Now, what's this next line? This next line is using pattern matching to bind whatever we're matching on to y. And then we're saying if that thing is even. So for example, if I put 2 in here, it's even. So we're able to have something like a switch statement, but actually include an if condition on if we wanted to. And you can do more ifs and ands, whatever you want. You can have direct matches like we had before. Sure, we can have 5 and say found it. And then, of course, you also can have a default case, like that's not covered by anything above. So this is showing it for for a numeric type, like you might see. So for example, languages like C have this, but we're going to show this going to be more general in just a moment, but I'll kind of pause for the initial opening of it. Yes. Correct. It evaluates to top to bottom. So yeah, it's going to try, and when the first case it matches correctly, it's going to do that and not consider future cases. Great question. So like, for example, this last one is the default case, right? So someone by rule will match anything that comes down there. And you'll sometimes see a lot of code. A defensive technique might be to have, the various cases they have, and then the programmer thinks it matches all cases, but there's some cases technically that mathematically are, still possible. They often use this case to throw an exception, right? They're like, if you get here, you should not be here, right? Like something went wrong. But other times it's totally fine, right? You want to filter out 2 cases and do this separately, otherwise treat the common case differently. Yeah, that's totally fine. You can use that. Correct. Yes. So let's go ahead and yeah. So to repeat this, I was told to change that to case 6 and whatever reached it, and the answer is no, because then they keep being precedenced out. Now, if I reordered it, it could, sneak ahead. Interesting question to run. Thank you. Cool. Okay. Let's take it one step further. So part of why we were so excited about case classes before was not just that case classes give you a lot. We can now combine case classes with pattern matching, right? So let's see a little example of that. In this case, we have two different case classes, represent vehicles. So we have, a submarine or a helicopter. Now, as two different case classes, those are two distinct types. We might want to somehow make those types be somewhat similar. So for now, we're going to have them both extend the same abstract class. We haven't talked a lot about inheritance yet, but for now, you can say they're both technically vehicles, although vehicle is abstract, so we can't instantiate it. Okay, but the point is more, we have two case classes. We go ahead and make up some example data, some helicopters and a submarine, sure. Let's go ahead and show pattern matching working on case classes. And what's cool is you have this very natural syntax where you can match on things. So in the minimum case, you can just match on types. So you can say, hey, for all these things here, I can just print out what I'm seeing, right? So if I see a helicopter, I'll just say, whatever helicopter's color is, it's a helicopter. If I see a submarine, I'll say it's a submarine. It's a good reminder, for example, that maybe before you even do that, one of the nice things about case classes, right, is we also can, they have a toString method by default, right? You don't need to make them if you don't have a certain way you want it, right? So if I want to just grab one of those elements, it's going to tell us, oh yeah, it's a helicopter and these are the fields, right? It tells you that right away. So that's given to you for free because it's a case class. We didn't write that. Okay, so we can match on types. That's what this one was. Sure, we matched on types, and for every types we matched, we kind of just print out what it was. We also can take the idea from the prior slide, start doing matches on not just types, but also attributes, right? So we can say, hey, I want a helicopter that is blue. So we're actually filling in the fields in the case class right here on the case side of the statement. And then there's some things that perhaps are variable, right? It's going to depend, right? So in this case, you're saying where's driver? We just implicitly defined driver. So when it matches in this case, if it does match on blue, it's going to then give us whoever was in driver as a variable now. And we can go ahead and print that out. And so in this case, we're saying, oh yeah, driver has a blue helicopter, right? So in this case, Laura has a blue helicopter, right? Okay, and then you can kind of see different types of syntax here. Here we're seeing, for example, we are matching directly on the case class. That works out okay. We can also match on the type and then, do these ifs like before, right? So we can say, hey, if it's a submarine and it's not, driving a yellow submarine, let us know. Or maybe we really do want yellow submarines. Okay, let us know, right? And so it'll tell us, oh yeah, Paul's got a yellow submarine. And then like before, of course, you also can say, you have your default case. So you can see very quickly with these pattern matching plus case classes, you can kind of quickly convey things and quickly respond to it. And so, for example, if you look at the code inside of Chisel or Fertile, it's actually really compact compared to a comparable compiler. And the reason why is a lot of the nodes in the graph inside the compiler for these various operations are all case classes. And you can pattern match on. Okay, I want to grab everything to say vec, okay, and boom, you can grab it in one line and get all the vecs that match a certain trait or something. So it's actually really cool. When you're building your own hardware, you'll often want to match on these in a few places, right? So where might you match in real hardware? You might match given parameters. Is an easier alternative to doing ifs and else sometimes. It's a more convenient way to kind of express certain conditions. Additionally, you might match if you're doing a much more sophisticated generator. It doesn't just take in numeric parameters. It takes in like a function or another module and then does something with it. You may want to respond based on that. Okay, if you give me a module of this type versus a module of this type, I'm just doing differently. For example, you give me a uint versus a vec, I want my generator to recognize that and then do the right thing, how it handles what you've given me. Cool. Questions? Okay. Let's apply this in one more way. So I think I told you this before when we did options, that options are, a way to convey the presence or absence of something very kind of programmatically and cleanly. And before we were doing this very verbose thing of, doing is defined and get, right? So for example, if we just take a sequence, in this case, I'm arbitrarily choosing to keep all the even numbers. So, if it's an even, sorry, all the odd numbers, excuse me. If it's an odd number, we'll say some number, it's an actual one that exists. And if it's, an even number, we'll say it's a none. So you can see, for example, this collection, 0, 2, and 4 are all nuns. So then if we go ahead and apply for each to it, we can see that, yeah, we can go through element by element, and if it's defined, we can go ahead and print out the value. So that's kind of very verbose. Turns out there's a few more ways to be more graceful about this. One is the fact that for each actually is going to skip over um, a empty element, right? So if I call for each on a none, it's not going to do anything. If I call it on something, it's actually going to do something. So that's actually pretty cool. So you can see, for example, or maybe if I go ahead and remove this at all and just see what we get. Okay, in this case, we're going to print something for everything there. But if you actually call it, because it's a collection, right? So collection is going to process every element. But if you give for each an individual element, if it's none, it does nothing because there's nothing there. And if you give it like something that's actually there, it'll actually do something. So you might see people writing code where you're reading someone's Scala code or Chisel code, you see them calling for each, or perhaps map, and the number of collections in the element should be like 0 or 1, or it's actually doing something on option. And the reason why is, yeah, option, it'll automatically kind of just filter it out for you. Now, maybe in a much more old school kind of style, maybe you want to just do a get or else. A lot of languages have some dictionaries, like in Python has this. For example, if you ask for a key that's not a dictionary, you can use this kind of method to make sure you get something back. It doesn't cause a key not found. Yeah, so for example, if I try to call this on a thing that has something, so we know that 1 exists, we are going to, the 1 should exist. Why is 1 not existing, right? Oops. Oh, it's down here. Yeah, we didn't print it. Okay, so yeah, we get the 1 out, sure. And then, for example, if it was 0, which we know is going to be a none, we get -1. Okay, so there's a get or else as a fallback. So depending on how you're using your code, maybe get or else is the most straightforward way to solve your problems. Sometimes you have these uses of for each or map. And I said the only reason why they're doing that is because it automatically filters out nuns. If you could also, for example, just call it on a you also can just call it on a collection. It's going to automatically, if you call flatten, it will of course remove all the nuns. If you're doing flat map, it'll also remove nuns. And so that's one of the reasons why I might do this. For example, if I'm doing an event, this is kind of the way to do it. And then finally, we can use pattern matching, right? We can say, hey, with pattern matching, given this element, for each element in there, what do we do? Well, if the thing is something, let's go ahead and print it out. Otherwise, we can say it's empty, right? We can go ahead and go through. So basically now we have multiple ways to interact with options that perhaps are more graceful than the original way, which was just, if is it defined and acting on it. Instead, you can imagine some of these other consequences, right? Question, yeah. Correct. Yes. The question was, what's the use of the underscore here? Yeah, it's good for me to go over and explain that. So as suggested by a student correctly, yes, it's the same as me taking a single argument and then applying it to that argument. So this is how we covered that, placeholder syntax for function literals. We're doing that here, where there's a single argument produced by this for each, and then we are just going to take that and apply that immediately with a match. Yes, question. Oh, great question. So the question was, didn't I say for each doesn't do none? So why are we getting none in some cases, or it was empty? So yeah, it's good for me to clarify. The difference between for each called on a single option versus for each called on a collection. So you call for each on a collection, it's going to go through every element. You call for each on an option, the implementation of option implements for each, and then they chose to do something or not do something, right? So one of these things where for each is not a language construct. That is a method implemented for all these various built-in types, right? And so for a collection, for each does what we're used to. For an option, it does this operation of either kind of filtering out or not. So for example, in this case, if instead of for each, I did for each again, so kind of a crazy nested case, for each inside, right? So instead of doing this, I said whatever that is, for each, and then I actually, I can just go like that, right? I think this is going to have the same result, right? Oops. Yeah, I was worried that happened. Okay, this one I have to actually uh, map out. So that's also going to work. So basically we did for each element, and now we're iterating on each option. And for each option, if we call for each, then we get that silencing behavior. With regards to this thing right here, typically the placeholder syntax does not work inside function boundaries. Oh, it did there. Sometimes it complains. It doesn't like it. So that's why I was like, worried I had to kind of go ahead and define it. And it just proved me wrong to show off. Okay. So yeah, so this, once again, even though we're having fun with functional stuff and learning what we can do, is this more readable? Maybe not the way it's used here. But more generally, we can see that as we start getting more comfortable with option, uh, we don't always have to do this kind of if process, right? Sometimes we can do things like a single for each, or a map, or a flat map, or something, depending on how we're going to interact with it. Cool. Any other questions? Okay. Well, that's it. I'll be posting homework for after this class when I get it almost done. Cool. All right. Well, have a good day, folks.